Alright, in this video we are going to look at something called generative adversarial networks. Generative adversarial networks. It is a way to generate, learn to generate images from a dataset. So let's start by importing some nice stuff. Alright, so now we have our imports. Let's try to look at here. So we actually, I didn't unpack it, so let me do that. Alright, so now we should have some more stuff. We have string and test. Let's see what's inside here. And furthermore, okay, so now we have a bunch of images. There's also some XML files. I think it's because this dataset is used for object detection or something, but we don't really care about that. So let's start by just looking at one of the images. So fruit, train, apple 10 JPEG, and let's show that, and let's show it. And we don't have that because why? Because we never ran this. And it's because we have to say from, and this is matplotlib. Okay, now we have those. So now we run it, and here is a beautiful apple. So we want to generate images like that. So let's set up the dataset. And let's make it a few more cells. Fruit dataset. Alright, so here we have it. I just pick out all the images both in the training folder and the test folder. We don't really have a notion of a test set. We're not trying to, do some kind of prediction. So there's no need to have a test set. And then I just load the image, convert it to RGB because we do want to keep the color this time, not like the last video. And then we transform it. So let's go ahead and give it a try. And like that. So we do get an image, and there's also a nice little warning. This is probably not going to work. It doesn't work because we need to transpose it. And how do we do that? So I think let's actually convert it to a NumPy object first, and then we want it transposed like that. And now here we have an apple. And also let's remove the axis. And let's actually do something else as well. Let's plot a bunch of these. So NumPy, and then flip around the axes and remove the axis like that, and then we go. Okay. And there's also a lot of clipping going on, which is kind of weird. So let's go ahead and do image like that, and let's print like the minimum of the image, the maximum of the image, and see what is going wrong. Okay, I forgot to import NumPy, so let's go ahead and do that. Right. It's kind of funny that some of the values are not correct. So let's also just do a clamp of the tensor to go between 0 and 1 like that, and then that warning should be gone. can remove the print statements. And here we have a bunch of images. So you can see it also contains cartoon images, and there's also pictures with more apples than one. So I don't know how well it's gonna work. So what we're doing is generative adversarial networks, and there's two things. There's a generator. Let's start with that. And the goal of the generator is take a random vector and produce an image. Then there's a discriminator. And this is a very neat trick that lets us actually train the generator. It takes an image and it tells you whether is the image real. So we're going to start with just a random generator, and it will produce like noisy images, just like random noise. And then we also have a discriminator. It will also not be able to predict things at first, but we can train it. Like we know how to train it. We show it a real image and we tell it this is real. We show it a fake image and we tell it this is fake, so it kind of learns like that. Train by showing a real image and making it output 1. And there's two steps, so showing a fake image and making it output 0. So the discriminator is kind of straightforward to train. The generator is a little bit more interesting. Like this is the trick. So we train this guy by generating a fake image and trying to make the discriminator fail. So we'll see how that works in a little bit. Let's start by making a generator. We'll make a super simple generator to begin with. So it will take a random vector of size 100, for example, and then it will output an image. And what did we say up here? We said 128 by 128. Yeah, sure, that's probably fine. So it's going to output image of size 128, 128. So let's try to define that. So class, and let me center it a little bit. So class, we'll just call it generator. Call it feed forward generator. It's just going to be super simple. We're going to have init, and I'm going to call it super init. And all right, so here we are. We have a simple generator. It has a linear layer, a regular observation function, a linear layer, sigmoid to get the pixel values to be between 0 and 1. And then we have this unflatten that takes the vector and turns it into an image. I think that should work, but let's test it. And we also need to put in what I've called the latent space size. That is the size of the random vector. So you cannot get it to work with 1. I've tried that before, it doesn't really work. And we're just going to use 100, I guess. Like that. And let's try to run a vector through it. So let's generate a random vector of size, latent space size. And actually, it should have, I guess we can do like this. There's one, I kind of think it should be this. Okay, so that works. What is the output? It is this. I think we had one too many of these guys. So here it is. It outputs a batch of size 1, and an image like this. So let's make a function called generator and plot images. It will take a generator and a number of images. Then we can calculate the rows. It's just the square root of the number of images. And the columns is going to be the same. Then we have here something like that. Okay, so we need to generate an image. So first we need the random vector. And we're gonna sample one like this, and it's gonna be 1, then space size. Then we're gonna have the generated image. We get that by feeding the thing through here. Then let's convert it to a NumPy array. Let's get the first one, and then let's transpose it so the color dimension is in the last one. We do this, we remove the axis, and we show them. So let's try to run this on this untrained generator. So we get 16 images, and cannot do that because we have to remove it from the computation graph. So that looks amazing, doesn't it? Looks really amazing. Just a bunch of white noise. Well, colored white noise. But you get my point. Okay. Before we can start training it, we need to define a discriminator. So here we go. It will also be feed forward discriminator. And here we have something like this, where we start by flattening the image to make it a one-dimensional vector. We feed it through a couple of layers, and in the end we output sigmoid. We use a sigmoid activation function because we want to output the probability of whether this image is true or false. Real or generated, sorry. And then let's create this guy like this, and let's run it through on a random image from the data set. So like this, and let me try to center this once more. And that did not work because why? Because again, it's assuming, PyTorch is always assuming that you have a batch. So let's make a batch. And here we go. We do get this weird, batch of size 1 with 1 number. So that, I think that's correct. All right, now we get to the interesting part. So let me go out here and we'll say train. So to train, we need a generator, we need a discriminator, we need a data set, and we need the number of epochs. We need to optimize both networks. So let's make an optimizer for the generator. It doesn't really matter which one. It doesn't matter too much, probably matters a little bit. Let's go ahead and do this. And this one is kind of the same, except it's on the discriminator. Then we need a loss function. And since the discriminator is producing probabilities, let's use the binary cross entropy loss. Let's use that. And then we can go ahead and set up the scaffolding. All right, here's the basic scaffolding. But now we need to set up some stuff. So first of all, let's find out how many, how big is the batch? Batch size. We can simply look at the shape of this thing and we get the batch size. Okay, so now let's generate images. So generated images, well, first we need the random vectors, of course. So generate some random vectors, normally distributed, and they need to be size, batch size, and then generator latent space size. So actually we didn't store that here on the generator, so I kind of want to do that. Because could be different for different models. So we don't want to hard code that. So we generate a bunch of random vectors. Then we can generate some images by passing them through the generator. And then a little bit later we are going to use them. All right. So first we train the discriminator. And we need a, so first let's run it on the real images. Okay, so discriminator, run it on the image batch, and we get some predictions. Now what should those predictions be? They should be 1. Like we said before, we want to output 1 if it's a real image. Okay, so then we can calculate the loss for this. So real predictions, real loss, sorry, real target, real images pass, and then we can go here and generate it images pass. All right. So generated predictions. Again, we run the discriminator. Now on the generated images, one more thing, we call detach, so that you can see that generated images depends on the generator. So it depends on all the parameters in the generator. But when we are training the discriminator, we don't want to calculate gradients for the generator. We're only updating the discriminator. So we detach the generator from the computation graph, so it's not passed. The gradients are not, updated down there. Anyway, so here is the target. That's going to be zeros, and generated loss. Let's say it's not the best number, best name. Sorry. So generated predictions and generated target, and then we can say discriminator loss is the real loss plus the generated loss. All right. So we can set the gradient to 0. We run back propagation and we perform a step. So that's pretty normal how you would train a classifier model. There's nothing too special there. But now let's see how we train the generator. So now we need the predictions of the discriminator on the generated images. And now this is very different from here. Well, it's not very different, but one thing is different. We don't call detach because now we want the gradients to go and propagate it into the generator network. So this time the target, the new target is actually ones. So we do it like this. It's a bunch of ones, and we'll call it the generator loss. The loss for the generator is how different is the prediction of the discriminator from 1, because the generator wants to try to fool the discriminator. So if the predictions are different than 1, which is the target, then we want a big loss. So that's the loss. Let's try to set the generator to 0. Let's add the gradient to 0 there. Then let's do back propagation, and then let's do a step. Then we also have this epoch loss. I'm going to add, well, let's have 2 things. So epoch disk loss, generator loss. These numbers are not super useful because of this thing that the discriminator tries to become better and the generator tries to make the discriminator worse. So it's kind of like a back and forth, and it's not guaranteed that the loss is always going down, even if the system is improving. So something to keep in mind, but still you can get some information from this. So we'll keep it. And this is called generator. We have to do that, generator loss. And here we should say discriminator loss and generator loss. All right, so now we have that. So it's worth just going over what's happening here again. We start by training the discriminator. We run it on a real set of real images and try to make the discriminator output 1. Then we run it on generated images and we try to get it to output 0 because it says 0 here. Then we add up the loss and we do back propagation and so on. That's where we actually update it, so the discriminator tries to output those things I just said. And then when we train the generator, we run the generated images through the discriminator, and then we try to update the parameters of the generator such that the discriminator outputs 1. So the discriminator, we're trying to make the discriminator think that the generated images are real. All right, let's make a data loader. Data loader is going to be on the data set. The data set is not, actually let's make it so, yeah, whatever. Let's do this. How big is the data set? 300 images. Okay, so the batch size, let's make it 16. We can shuffle it because just in case there's some good stuff in there. Let's make the generator. It's a feed-forward generator, and latent space size is 100, let's say. The discriminator is the feed-forward discriminator. Doesn't have any input arguments. Then, just to keep it like, let's make it systematic. Let's generate and plot some images of the generator, 16 of those. We do that. Again, it's noise like we saw before. Now let's train, and what was it? It was generator, discriminator, data loader. Okay, so generator, discriminator, data loader, and then let's say 10 epochs. And these are, they were not called that, they were just called gen and disk. Let's try to run that. Okay, so it hasn't failed yet, and let's see what happens. Actually forgot an important thing, which is let's move this stuff. Let's first set them to training mode, just to be sure. I think they are training mode by default, but I don't wanna risk it. And then we do this. All right, see you back when the training is done. And of course, if we do that, we also have to move the image batch to the GPU. Let's try to run it, and that's because everything now has to go to the GPU. This one has to go, this one probably has to go, this one has to go to the GPU, this one. Now it's running. Okay, see you in a bit. All right, so it kind of degenerates into this case where the discriminator is always wrong, and because of that, the generator, or basically the discriminator always predicts that the target is, the image is true. Because of that, the generator has no loss and it doesn't learn anything. I tried to look at the code to see if I could figure out what's going wrong, but like it seems completely correct. There is a chance that the models we made just don't work. So let's try some more advanced models. And gonna use convolutional nets. Alright, so I defined some convolutional nets. You can see they are quite big. Let's actually, I really should write a function for this. Like that, and like this, and it's gonna be the discriminator. And let's divide it by a million. Divide by a million. And you can see here the generator is 200,000 parameters, the discriminator is quite a bit larger. So before it's trained, it just outputs some noise like this. There's a little bit of structure, like it seems a little bit green on the edges, and there's some lines you can maybe see. If we train it now, let's see what happens. It outputs something that is not completely degenerate like before. Like here it was just, you know, one was always wrong and one was always right. So now it looks a little bit more natural. So let's try to run this for 10 epochs and see what happens. All right, here we are. It's finished training and it generated some images. So I don't know about you, but to me this doesn't look like fruit. Let's try to run the models for a bit longer because they are quite large. Let's run them for 100 epochs. And then we can talk about it after that. All right, train it some more, and we get something like this. Like it actually looks slightly more correct. Like there is some kind of shape here that is somewhat correct, but we might be having an issue that the model is just too weak to do it. So we also saw here that the generator has not that many parameters. 200,000 is a lot, right? But you get what I'm saying. All right. So to fix that, let's just try to crank up some of these numbers. Let's crank them up. I don't know. Let's try this because I say so. So double the number of parameters. I think that's a good start. Let's generate some images, still weird and random. Let's run this one with just 10 epochs. All right, so it didn't really produce amazing results, but interestingly, it did change the output. There is some kind of weird patterning going on here, so I think we should try to fix that. What happens if we do this? Then we don't get quite the right shape. And we can do this, then we get the right shape. So let's try that. It doesn't change the number of parameters. The images are looking okay, maybe. Let's train it again. Let's see what happens now. All right, didn't noticeably change anything. Let's try to crank up the parameters some more. So here, probably keep 128. Actually, you know what we should do? We should have filter sizes. That's just a list of things. So first we go to 64, then 128, then we do 128 again, then maybe we do 64, and then we can do 32, and that's it. So this 64 is filter size 0, and if filter sizes, and here is, oops, that was not correct. Filter sizes 0. And here we go, filter sizes 0, filter sizes 1, and filter sizes 1, and so on. All right, so I added those in, and now let's check the number of parameters. Now it's like 3 times the original. And still, let's try to make it almost comparable to the discriminator model. We'll do something like this. That's now it's actually too big, so how about this? Now they're roughly the same. Actually, the generator is a bit larger. I'm a little bit afraid you can see this kind of pattern here that's structured. That should not be happening. But let's try to train it anyway and see what happens. Didn't really help. I think it pushed the loss down a little bit more. So just because of that, I think I'm going to rerun this long-term training. And I will see you when it's done. All right, here we go. We trained a bunch. The error is around 3, whatever that means, which is a little bit lower than what we ended up on before. It still doesn't look like fruit. I am actually going to go crazy and train it for another 100 epochs. And yeah, I will see you in another 7 or so minutes. All right. It trained. We kind of not really learning anymore. Like something's going wrong, and yeah, you can see doesn't really work. So let's make it bigger. Let's make it even bigger. Good. And this is going to be, whoops, what am I doing? Filter size is 5. Here we get 5 as well. Get 5, and it's gonna be 28. And well, now let's keep it 64, and then let's do 32. Still works, and we got hardly any extra. Sorry. Okay, so no. Okay, so this doesn't work because now the image is like way too big. So we gotta do something like, what am I doing? Something like this. It's like possible to see the full thing. Okay, here we go. Let's set the stride here to 1 as well. And now it still don't work. So what happens if we set this one to maybe 2? Then it's 64. Then I think we can say 0 and we can say 2 maybe. Yeah, so that worked. All right. We added another layer, didn't add so many more parameters. Now it's like red on the edges. I don't know why, but we'll go through this thing again. So see you in a bit. All right, so that didn't work either. I have refactored it a little bit so we can change the size of the images more or less easily. So actually what I am going to try is to, where did I put this crap? Well, let's open this outline and go to the dataset. Let's try with really small images. Okay, let's try that. So here they are, you can see they are quite downsampled now, but it should be a lot easier to learn. Now we can just try to, actually let's restart the full kernel. And then let's run everything from scratch. That's not so interesting. Okay, got the data set. We define the feedforward generator stuff and so on and so forth. Still, now you can see it's kind of like pixelated, more pixelated. And here we go, that's fine. Not sure why I have this, but whatever. Then we go into training. That shouldn't change. Maybe the batch size should be larger. I don't know. Let's do this again, and now let's train this simple feed-forward model. Alright, so that went a little bit better. I think last time it just degenerated, but now it actually kind of works. Okay, so this is a lot better. You can see it kind of looks like an apple if you don't think too much about it. So why don't we run this one a lot more? And let me put in another cell that runs after. And so even after 100 generations, the model's still quite crap. So I think it's time that we pull out the convolutional nets. So now, of course, because I don't know how to automate this, but we need to make sure the output shape is 32 by 32. So maybe let's do something like this, and let's replace kernel size equals 4 with kernel size equals kernel size, and same here. And now we get 30, so that's 34, and then I think if we add a padding here, then it becomes 32. Yes, and that one didn't work either. Yeah, because the scaling here is all wrong, so we need to. Can I comment it? No, I don't know how. Whatever. All right. So I think, yeah, here we get scaling. So here it should be like 16, 8, sorry, 4, 2, and 1 even. So if I do, can probably get rid of this layer, and then we say times 2, and that works. Okay. They're smaller now. The images look fine. It looks random to me, at least. Let's try to train them. So this is how it looks after 10 epochs, which is not great. So let's give it some more. All right, let's give it a look, and it's amazing, just amazing. All right, let me think. All right, I have given up on generating fruit. So instead, we're going to try to generate some numbers like this, and it kind of already works. You can see it's kind of like only figuring out 3 and 8, but whatever. Let's go down here with the more fancy models, and they should have the same number of parameters, just some images. Let's try to run this, and I'll see you in a bit. So actually, before I go, one thing to note is that there's a lot more images. That also has an effect, and it's simpler. There's only one color channel, so something to keep in mind. Alright, so I stopped the training of the convolutional net because you can see here the error started exploding. And this is what it's generating at that state. So that's also not great. This doesn't look like any numbers that I know. So final thing we're gonna try. Yeah, see you in a bit. Alright, so I have this this pair of models that I used on MNest, and I have tried to do this before, so I know it works. And as you can see here, I trained them for 10 epochs, and we already get something that looks like numbers here. It looks like ones mostly, but it should be better if I train it for more. So now let's try to, first of all, train it for some more epochs just to see what happens. And then analyze what is the difference between this and what we did before, because I really don't know. It should be just as good. Yeah, so let's do that. Alright, so let's try to think about this. We have this network. Let's copy that and let's go have a look at the other one, other generator, which was this one. Just gonna plunk it in here so we can easily compare. So we have the same kind of thing here. We go to 128. Kernel size is the same. Stride is a little bit different, but honestly I wouldn't expect that to make such a huge difference. Here we have batch normalization, also ReLU. We have sigmoid instead of tangent hyperbolic, which I also would expect is fine. So I don't see a huge difference there, okay? Alright, let's go and look at the generator, the discriminator. Starting to use the mouse, like should tell you something. So this one, that's actually exactly the same. Somehow I made it exactly the same as before. So it's definitely not that. Now wait, I think I fucked up. Yes. I think I fucked up. So let's get this stuff. Then we go up, up, up. Right, okay, it's definitely not the same. So what do we have? We have a convolutional. It has a lot more filters to begin with. We have ReLU, then we have, and this one doesn't have any batch normalization, so that's interesting. Could be that batch normalization is ruining it here. So in order to test that, well, let's look a little bit more. No batch normalization. We flatten. There's only one linear layer in this one, but that shouldn't be a huge issue. Let's comment out the batch normalization here. It's also kind of snuck an extra batch normalization in there. That's not so good. Let's put, okay, whatever. Let's put that there, and let's do this. Okay. So let's try that. Now I want to go on the top. I need to restart this stuff because I took a short break to have lunch. All right. The image size potentially cause issues. So far so good. And I forgot to run the line that defines the latent space size. This is this one. And here we go again. Okay. And we also didn't do that one. Generate plot images. Just trying to not run everything again. Okay, probably I didn't run the train either. Yes, I forgot that one as well. So that one has been ran, and we should also run the data loader. And now I think we can go finally. Train. There we go, it's running. Let's see what happens. All right, so I stopped it up after 6 epochs, and I think from now on we're just gonna train for 5, and it kind of degenerated into this thing. So my next idea is that the dataset needs to be normalized to have a different range. So before the images went from 0 to 1, if we do this, they will go from -1 to 1. So they will look the same when you plot them, because that's just how that plotting thing works. But one other thing we need to do to get it to work is to change this one to tangent hyperbolic. So the output is between -1 and 1, and not just between 0 and 1. Everything else should be the same. This is kind of okay. Let's run the training and see what happens. Yeah, I think we're good. So let's go here and let's see what happens. And here we go. Here's the train for 5 epochs, and it has kind of collapsed onto only producing ones, but it is actually producing something that looks like it could come from the dataset, which is just insane to me. Like, why is it such a huge effect that the data goes from -1 to 1? But it is what it is. I mean, the thing is, people say that training GANs can be very difficult. And I've also seen myself that if we take this one, if you remove the batch normalization, it just doesn't work. If you put in layer normalization, it kind of works, but a lot worse. Yeah, so like it seems like they can be quite finicky, these generative adversarial networks. I might try to finish up the fruit generation off screen, but I think this is it for this video. And I'm pretty sure we will take a look at other generative AI methods in a future video. But until next time, bye bye. All right, so it's now a few days later. I actually went back and went over it again. And one of the big issues was that the images had pixel values going from 0 to 1, and that kind of interfered with these ReLU activation functions and the linear weights being initialized like they normally are, with both positive and negative values. So what I went in and did, I renormalized it so the values go from -1 to 1, and then I ran it, and now it kind of works. So, and you can probably make these models bigger to get better results, but let me skip over these linear models and let's look at the convolutional models. So if you don't train them at all, it kind of looks like this. And if you train them a little bit, it kind of looks like nothing at all. You train it much more. So there's 100 epochs, but remember it's quite a small data set. So I think that's also another factor, that these kind of generative models, they need a lot of data, or they need to see the data a lot to really learn something. So train it a bit more, it kind of starts to look maybe what a fruit would look like in a fever dream. Train it even more now, kind of apple-ish, train it even more, and train it even more. It kind of starts to look like an apple. You can see there is some red, yellowish thing, and there's some green thing on top, the leaf on top. And yeah, so that's it. That's where we're going to leave this project now. Maybe we'll return to it another day with some other data. Yeah, so see you in the next one.